We will start our journey together throughout these 20 questions with a question on our wireless cellular mobile network. And this shows a typical picture of a cellular network. The entire physical space is divided into many cells, a hexagon area here, with a base station here and many mobile stations, like your cell phones or tablets. And in this course, we ask the question, how does my smartphone work in CDMA network? In both main versions of 3G networks, CDMA is a key component of the technology. Okay. And we will look at two critical issues. Number one is a tactical one. Okay. How can we control interference in the air? Your signal will cause interference to my transmission, just like in a cocktail party. Well, maybe controlling the transmit power is a degree of freedom we can use. And that is something we'll talk about. Transmit power control, including a very simple but clever algorithm that can distributively control the transmit powers so that we don't end up shouting at the top of our lungs altogether. And this is the algorithm that was implemented in all the 2.5G and 3G standards. And this shows us a particular way to control what we call the tragedy of the commons, or so-called negative network effect. Another purpose of this lecture in answering this question is to introduce two powerful modeling methodologies. One is called optimization theory. We'll look at a special case called linear programming here. Now, optimization is something we do all the time in our daily lives. For example, if you want to maximize your happiness and your degree of freedom is to choose between taking this course versus going to the movie theater, okay, and the constraint is you only have limited number of hours each day, you may decide to pick one or the other. And optimization theory is a mathematical way to make precise many of those English languages. We also introduce, in addition to constrained decision making, a model to think about strategic behavior of intelligent agents, which could be human beings, which could be networking devices, and that's called game theory. We introduce the basic terminology of both, and both will be used a lot throughout the course. And indeed, in next question, which is how does Google sell its ad spaces on a search page, we'll be using game theory to model and analyze a particular mechanism of allocating resources, in this case ad spaces, and that mechanism is called auction. Now, auction is something that some of us are familiar with, and we'll look at different forms of auction, how an object is allocated among competing buyers, and what price shall it be charged for. We'll look at a graph like this, so-called bipartite graph. Now, skipping the details to the actual lecture. In this preview, suffice to say, there are many potential buyers and many objects, and we need to find a match. What kind of match will provide a fair and efficient allocation? That is the question we have to answer. And we'll look at examples from Google as well as from eBay allocation of a single object. We'll see that a smart idea is to say that object, if there's only one, goes to the highest bidder, but the price is actually charged based on the second highest bidder's price, which sounds very counterintuitive at the beginning, but we will see this turns out to be a smart way to mitigate the negative network effect, or to so-called internalize network externality. Now, of course, Google's main business is provide a search service and to provide a ranking of relevant web pages to your search query. Now, how can Google rank relevant pages? Let's say there are 4 relevant web pages. The actual problem is much bigger scale than this. But suppose we have just 4, and there are some links among these nodes. The nodes are the web pages. Each link is a directional hyperlink between one page and the other. Now you might think if a lot of pages point to a given page, that page should be more important. Turns out that is a good starting point of a line of thoughts that led to what's called PageRank algorithm, named after one of the 2 co-founders of Google. This is a powerful algorithm. We'll see an efficient way to execute it and to compute different node importance scores. We'll pick up this theme later in Lecture 8. We'll also show how PageRank by Google is strikingly similar. In fact, there's an exact mathematical parallel to Qualcomm's CDMA power control algorithm. And we'll see that while the networks are very different, one is a web page network, there's a wireless device networks, there are many underlying commonalities in how they treat the challenging problems there. And then we'll move on in question 4 to Netflix. If you have used Netflix, whether DVD or online streaming service, you have noticed that Netflix recommends movies to you. How does Netflix do that? That is the question. And we will talk about the interesting story behind the famous Netflix Prize, an open online international competition a few years ago, where Netflix offered $1 million for teams that can do a better job of recommendation. We're going to define what is the job of a recommender. Specifically in Netflix case, what is the figure of merit? How can you compare one recommender's performance versus the other? And it turns out a powerful idea in the winning solution of Netflix Prize is collaborative filtering. It leverages the fact that different users have different similarities and in their behavior and their tendency to like or dislike certain movies. So if I want to estimate how user 1 might like certain movies that she hasn't watched yet, I may actually leverage my knowledge about the other users' ratings of this movie. And we see a smart idea to leverage that understanding to enable a very accurate recommender system. Along the way, we will also expand our portfolio of optimization theory from so-called linear programming, LP, to the so-called least squares, which is a nonlinear quadratic optimization. And we will see how that extension can be carried out. Now, question 5 is something that perhaps all of us have encountered. We probably have all used Amazon to do some shopping online. And when you go to Amazon, let's say I want to buy a new HD TV, you see there are 2, or in fact many options. Okay, now one product may have 3.5 stars, the other may have 5 stars as the average number of stars in the ratings. Now you may say, well, looks like this is a better product by average rating count at least. But suppose I also tell you, which Amazon does, that there are 500 reviews behind this average, and there are only 2 reviews behind this average. This is a little extreme case to illustrate a point, but in this extreme case, you can say that, well, then I'm not quite sure if I should trust this average of 4 stars anymore, because somehow the sample size is not big enough. Okay. Whereas there are 500 of these, maybe this is more trustworthy, and I'd rather prefer this 3.5 star product. So when can we trust an average rating? And how can we incorporate the size of the reviewer population? And do we trust that 500 reviewers will all be independent in the way that they evaluate? It turns out that assuming independence and unbiased opinion, there's a very interesting way to incorporate the size of the reviewer population in the so-called Bayesian analysis. And we'll see how ranking can change once you take that into account. And we'll try to reverse engineer how Amazon does the job by looking at the trend of the review scores, by looking at the size of the review population and the reputation of the reviewers. Now, these are what we call opinion aggregation problems. Okay, we try to summarize different opinions by many different users in the network into a single number. And we know simple averaging doesn't always work. Now, opinion aggregation becomes even more challenging if the resulting aggregation is a binding resolution. So in question 6, we'll ask, how could Wikipedia even work? Now, Wikipedia, as we all know, is a free, open, online, and dynamic encyclopedia. While it has many limitations, it by and large had worked very well over the years. Now, one of the issues is that for certain articles, there's a lot of debates, certain political, religious article, for example. So how can these contributors and the editors come to any agreement? How can they form consensus? And we're going to look at consensus modeling through two things. One is voting, the other is bargaining. We'll look at the classical result on voting theory, okay, by Arrows. It's an impossibility result that says that even when you are facing a very mild situation, okay, for example, all the votes make perfect sense, you can still come up with a voting output, the final voting results, that doesn't make sense. For example, if there are 3 candidates, A, B, and C, then the output may say that A is better than B, B is better than C, and C is better than A, which is a cyclic and therefore logically inconsistent result. And we'll look at how that could become the case and how we can better internalize so-called network externalities to enable a more meaningful voting system. Then we'll also look at bargaining, okay, how two parties can bargain to try to reach an agreement, even though the agreement points may be different and therefore their individual utility or payoffs or happiness will be different as a result. Now, consensus formation is a tough subject, and we will see some gap between the theory and the practice. Now, that gap actually will become even bigger as we go into the next 2 questions. Question 7 is on how can we viralize a YouTube video. Now, understanding the viralization of a product, a service, art, is something that is very important and yet hard to accomplish. Now, we will take a look at a particular model for viral phenomena in a crowd where independence of opinion breaks down and we have what we call cascade of information. After some point, everybody simply follows what's already been done by the crowd at that point. For example, you may have one guy on the street corner with a nosebleed and decide to tilt his head to look at the sky. And then if you got a few other people tilting their heads, then you may see that many people start to aggregate and cause a cascade. They all start tilting their head towards the sky to see what's going on up there. So this behavior of people ignoring their private signal to follow the public actions before them is one model of viralization that we will see. And we'll also see some kind of influence model that describes synchronization. People start to behave with the same face. We'll look at models that talk about influence on a macroscopic scale. For example, when Apple first introduced iPad, maybe only 5% of the population use it. But then it started to become more and more popular, and eventually it may reach a certain equilibrium. Okay, maybe say 65% of the population will be iPad users. So how can we model understand that behavior? That will be question 7. And question 8 continues on influence model, but this time with the help of topological information. That is, we will know who connects to whom, and then we want to understand which nodes and which links are more important or more central or more influential than others. And a very famous story goes back to the Renaissance Italian families in Florence, where everybody appreciated that the Medici family was by far the most influential. But if you just count the so-called degree, that is the number of neighbors this node has, it's got 6 as the degree, which is indeed the largest, but there are also families with degree of 4. Okay, and if you just look at the 50% difference, that hardly describes the much higher influential power of the Medici family in this graph of family relationships. So how can we understand other notions of node importance? And then how can we use that to understand phenomena such as contagion of opinion, okay, based on the local topology of a node, and to understand infection, including actual infection of diseases. And we will see an example of how certain diseases can be treated by providing enough immunity in the population so that it does not start to become a pandemic at all. We will also take a look at how do we define different groups in a network. Okay, if I give you a Facebook network, how can you divide that into X number of groups? Now that is an interesting discussion of the impact of connectedness, or the topology, who connects to whom, on the functionality of influence. And then in the next 2 questions, we'll be dealing with 2 famous topological features and the relationship between topology and functionality in the network. Question number 9, we will ask ourselves the question raised by many people and then codified by an experiment by Stanley Milgram in the late 60s, the small world network. In Milgram's example, okay, he tried to give a letter and ask people in Nebraska to find a way to send it to the destination, which is a suburb in Massachusetts. And it turns out that among those actually eventually arrived, the median length of this chain of search is actually very small. It's actually, the median is 6. And that led to this famous 6 degrees of separation. In late 2011, some people measured the degrees of separation on Facebook at that time and said it's actually even smaller. It's under 5. Now, what does it mean to say there is a link between 2 Facebook users? That's another debate. Now, but we're going to look at why this small number is a surprise. And we see it's a surprise not only because there are short paths, but also there are short paths despite the fact that in many social networks, like nodes tend to aggregate, and therefore your friends' friends tend to be your own direct friends already. Despite that, there are short chains between any 2 pairs of any 2 nodes in the pair. And even much deeper than that, we'll try to explain why a greedy routing methods, like in Milgram's experiment, could lead to a discovery of short chains. So it's not just about the existence of short chains, but also the computability or the discovery of some short chains using only very limited local information. And that is the true surprise we try to explain through different models of small world networks. Another famous topological feature is called the scale-free network that has been observed in many kinds of networks, including biological networks, social network, and certain technological networks, like the internet router graph. Now we'll say a few words about why those measurements might have a problem. But let's assume that the internet's router connectivity pattern does follow the scale-free feature. Now, what is scale-free? Roughly speaking, it says that if you look at the degrees of all the nodes in a network and you tally that into a histogram, you will see what's called a long tail distribution, which is very different behavior than a typical, say, Gaussian or normal distribution. Okay. There are nodes that have a huge number of degrees. Now the question is, where are they? In year 2000, there was a rumor that says the internet has an Achilles heel. These extremely highly connected routers sit in the middle of the internet, and they become an easy targeted attack. And if they are taken out, then the internet is broken into many pieces. Now the question is, if we call this kind of vulnerability the Achilles heel vulnerability of the internet, does the internet actually have Achilles heels? And the answer actually is no. While the internet has many vulnerability and security and privacy concerns, it does not have this particular type of vulnerability. It does not have an Achilles heel. In fact, the highly connected nodes of the internet tend to sit on the edge of the network, and those routers in the core of the network tend to have medium to sparse number of connectivities. And this interesting story, the lack of the Achilles heels on the internet topology, illustrates a very important message, that not only you have to look at the graph or the topology of the network, but you also have to have domain-specific models on the functionalities. In this case, the functionality of performance maximization under router constraints, in order to have a meaningful conclusion about networks.